Okay, the floor is yours. Thank you.
Thank you. All right. Okay. Hi, everybody again. Sorry for little disruption. Usually happens when you're in the remote mode. So, okay, today I'm going to talk about the from the teaming concept. What are we going to do about the predictive maintenance, and what are the foundation layers of the predictive maintenance of the electrical vehicles? When I do that, actually, I would like to talk about what we have learned from our previous projects, because we had been working recently as AI for Sec in the many electrical vehicle projects, namely Opeva, Escalade as well. We are also working on as a team this EU pilot. It's the RISC-V base HPC AI accelerator platforms. So what as a team, our goal is to blend about what we use in the different EU programs, and to learn and to basically try to add on to what we had learned so far. So that's what I would like to, basically give you a summary about what we see as this, why this predictive maintenance is important, what are the layers, and how we tackle this problem in for the electrical vehicles. So. Okay, today I'm going to talk about the digital twin of predictive maintenance for electrical vehicles. During the course, with working with RRG, especially with Alper, we tackled this digital twin framework issue. I mean, we started with the original two small short diagrams, and then we find that these are do not entirely good for our needs, for our complex requirements. And then from I think from month to month, and the from one work package to another, it improved a lot. And actually, I want to show you what is our view of the digital twin overall, and how we approach this electrical vehicle for any issues like predictive maintenance can be one, fleet management is another one. But I think we wanted to define a good architectural view of the digital twin of these assets of the electrical vehicles, and I want to show you that. And the next one I would like to show you is, okay, what are the things that we tackle with the predictive maintenance, and this is clearly written in the teaming proposal. And these are mainly the batteries, power electronics, electric motors, powertrains, and things like that. So I mean, and then there are a lot of factors that influences the remaining useful life of those components of the electrical vehicles. And the vibration is one, road conditions, driver behavior, and the traffic also very important one. So there are many internal and external factors that influences the predictive maintenance, and we are tackling with that during the course of this our current other projects as well, Opeva, Escalate, even in this accelerator work in the EU pilot. And what are the techniques that's in use today? I mean, one of everybody knows this LSTM now. It's a RNN network, but what are the other techniques that's coming, that's becoming popular? Even like the last 6 months or 8 months, 9 months, when we started this predictive maintenance work, I mean, even the literature has been changing a lot. I mean, there are other things like the energy efficiency of those algorithms. I mean, you don't want to basically, consume all the energy while trying to maximize the energy of the vehicle, right? So basically, algorithm efficiency of the energy efficiency of the algorithm itself is also very important. And recently, lots of researchers are tackling into that. Basically, I mean, we started with the comparison of those algorithms. Now we are also trying to optimize all those algorithms, make it most efficient for the hardware, and even we are looking at what kind of hardware we can use to tackle this problem. I mean, especially on the vehicle itself, the energy and resources are limited, so that we wanted to see and we wanted to look at the trade-off of accuracy to do energy efficient, the power consumption. So I think performance per watt is one of the most important, KPIs of the world today, and it's happening everywhere. Because I think I'm like right now looking into 8 or 10 EU projects, and most of them, all of them, is looking. Okay, you want to optimize, you want to have a great latency, and throughput, but what is the energy? What is the power that you're consuming to have this accuracy and to have this great output? So I think that's very important. And finally, and maybe also very very important is the explainability. I mean, if you have an AI that produces some output, but if you cannot explain what you are producing and you don't have anything to show, and maybe that AI is not useful at all, and maybe that has got some bias or other issues. So I think the explainability is one of the most important issues, and how you explain it is another factor. I mean, the sometimes explainability algorithm itself is very unexplainable. I mean, so I know if you work with the Shapley, Lime, all those algorithms, some of the outputs of algorithms are maybe not so explainable. So making heat maps, other scatter matrix, scatter plots, and things like that. I think it's our job to make it explainable, so to show that really AI is working as it's supposed to. So okay, this is the motivation. Okay, I would like to show you the main figure of the what we had learned, how to draw a digital twin of an arc, of an electrical vehicle or megawatt charging system or any asset as such. Okay, the on the lowest layer there is this physical asset layer. That's where the sensors are, and here you're seeing the energy, where the energy is coming from, the chargers, as well as the vehicle itself. So this is the physical asset layer, and all the sensors are located in here. In the level one, there is this communication layer, data acquisition, and any protocol that basically collects the data out of this data acquisition layer, MQTT, REST API, and these are just few of them. So another one is the communication protocols, any IEC protocol or CPP that's using for charging system, or the communication layer protocols that communicates the edged cloud and things like that is the protocol layer here. Also on top of it there is this data storage layer. Alper just explained, this is where the ontologies resides and the metadata resides, and this is the, like, usually we use MariaDB, and if we have a larger big data, we use Hadoop or things like that in the data storage layer. Sometimes this is distributed, sometimes it is just in one place, like then in that case we use MariaDB. And that's where all those ontologies reside in this layer. And here, for example, recently, in a very recent, like a couple months, these LLMs are becoming popular, and this is where these vector databases are residing. Give you an example. So I think this layering is really great and nice to basically sort of explain, what is the, how your architecture, how your components interact with each other. Okay, that's the most populated layer. On top of it, data storage layer is a service analytics layer. This is where our predictive maintenance algorithms mainly are, and all of the data processing, digital representation, and the synchronization between physical and virtual world. Any synchronization algorithms, any AI algorithms apart from the predictive, that can serve for predictive maintenance, that can serve for any other things, any foundation layers that's for the digital twin, the frameworks, middlewares, and all resides on this L3 layer. And last but not the least, this visualization layer is the key, because if you cannot present your digital twin, it's not really a digital twin. So that's where the different methods, like the model-based visualization, metadata is, you have to show the metadata to see whether you're portraying the overall ontology, overall concept properly, the workflows, and the visualization of the data sets. And I think, as we discussed, we found this very nice. And there are also two other layers that's like the perpendicular. horizontal layer, sorry, this security and privacy layer that covers all and each layer, so that this needs to be addressed for anything, for any architecture to cover the digital twin. Without that, it's not complete. Of course, with the requirements of the EU, of the GDPR, and the security, of course, any security from the communication, as well as this, like anything that from the encryption from the data, and even on the top about the how you can protect the your visual data. So these are very important from the digital twin concept, and we found it very usable, and we apply it to all the projects about this digital twin easily to the programs, and this is what we want to use. We are using for the teaming as well. Okay, let me go to the second one. This is another way of looking at the problem. This is a little more detailed looking at the problem. This is how we define in the recent papers with Alper. We had like a manifest papers recently. And in that, there is this edge layer. That's where this IOFOC and edge layer, IOFOC resides. That is all the policies and X by design on the edge happens. This IOFOC is, you may know, it's a microservices-based, nice edge platform framework, I would say, that covers all the dealings with the edge and cloud. And then there is this arrowhead layer that's the microservices layer that has all the communication and all these learning layers and there is a federated learning, and it has got interoperability and standardization. Mimosa is becoming a very important standard for the condition-based maintenance and the predictive maintenance, and it's becoming heavily used, and it provides a good ontology and semantics for defining the predictive maintenance, and that's what we are using today. And we have those, MariaDB and all the semantic backend defined in the database. That's where also this decentralized enterprise layers are. And then finally, this is the execution business layer, all those visual interactions. You can have the Unity and also Plotly, all your graphs, and all your simulation happens on this execution business layer. If there's a need, you can have the AR, VR tools as well in that. I think this explains overall how the layering are for any predictive maintenance. And in that case, for example, as I'm showing on the right, there is this battery, BMS, powertrain, the cooling, and all those components. And this is an example for fuel cell as well as the battery. The same hybrid vehicle I'm showing here, but it can be battery vehicle as well. And okay, this is a little bit more detailed picture that shows the other factors like the weather, road conditions, the charging, all the security protocols, and the resilience layers. It gives you more information. In here we show also the charging infrastructure data, as well as the road conditions, and even here we work on the driver behavior and try to portray the driver behavior in the 3D visualization work that we are doing with Carla as well. So just for the simplicity, I'm not showing that, but this is the overall architecture, I would say, of the predictive maintenance framework of overall in the system. Okay, so going back to the PdM, here I'm going to show you the battery only, because I don't have time to because predictive maintenance is not only for battery, because there's this powertrain, power electronics, charging system. Yeah, but this one I want to show you. The one approach, the traditional approach, the database approach, because there is a new approach with physics information learning. Our colleagues from CEA is going to show that. Here, there's this data about the voltage. This is a time series data, the voltage, current, and the temperature, and the SOC. And basically, looking at the time series, we do data analysis and regression, and we select the decision tree models, and we load the models, and we do correlation, feature selection, and hyperparameter tuning, and then we do rule estimation based on the different techniques. And this is we had contacted this with the open set data of the 20 vehicles that has been available for the 9 months, and we come up with this SOC and the SOC prediction with the the different techniques. So that's all I would like to show you about. This is the general architecture of the database approach to the predictive maintenance in the framework that I just showed you in the previous slides. Okay, this is a more detailed slides about how these are, how things are work out, and I mean here, I mean we use some of them, and we are still working on the other of them. So we look at it's basically feature selections. Also, we do try to do, we look at, we measure, for example, in one of the cases, we measure with the CNN, and we found some issues, and we tried using hybrid LSTM with CNN. We get better results, and we tried the other techniques as well. But I would like to show you in one slide, in a nutshell, how things are, comparatively, how the SO6 and rule production techniques are used for the data approach here. But we look at the MAE or MSC. These are usual suspects for the KPIs, for the values, accuracy. But we also look at the performance for what? I mean, what is our performance for the, for the power that we consume, which is very important. And we look at the both training as well as the inference. Focusing much more on the inference time, the prediction, basically, because that's what we do mostly during this is the most important decision, for the SOS estimation, also in the range estimation techniques. Okay, these are some of the outputs on the right side. Without spending much of the time, you're seeing we compare the algorithms. I mean, we don't only run the algorithms. Of course, we run the algorithms, but we also compare the algorithms for the energy consumption. We use the prun libraries available by open source, and we basically, when we compare them, we found that XGBoost 2.0 produces better performance per watt than others, while comparing good or better accuracy, comparing to other algorithms, LSTM and others. So that's why we decided to pick LSTM, maybe with random boost, to implement the pruning and other energy efficiency techniques with TinyML to go further analysis and to port over to the other architectures. This is what, okay. This is also, as I showed you, very important. What is the, which parameters, which input parameters, and which other factors that influences the output of the AI results? This is what I'm showing here. You're seeing the feature matrix and the SHAP values, and how how one variable individual contribution of the features impacting the final prediction in these cases. This is just a Atalay output, but you can try any other output, which is very important when we try to explain, how your AI algorithms works. Okay, so here I want to show you, as we just started, what are the things we would like to be doing. We will be continuing. We are going to be doing model pruning techniques for the algorithms that we are selected, which is the XGBoost and random forest. And we want to focus on other techniques as written in the objectives of the teaming, which is the powertrains. And we would like to collaborate with other partners like CEA. We want to focus on the TinyML implementations, and we would like to also use this RISC-V architectures, like EU pilot. There exists that we are working the vector chiplet and the MLS chiplet, and we want to do offloading techniques and the pipelining and vectorization techniques that's available from this hardware, and we want to get the best out of them, and for the both EU projects. So yeah, that's all I would like to show you. Yeah, Alper.
Thank you very much, Serdar. So it's really a nice presentation. Is there any question from the audience about this presentation? If not, I will have one.
Yes, go ahead, Alper.
Yeah, I'm curious about the use of these large language models in this PdM domain, Serdar. I know that you've been working on this topic. What are the, how do you see its future? Can it be used by the, maintenance workers? Is
Great
only
question.
the explainability is the main thing, or what kind of advantage it may bring?
It's a great question, and it's a very hot question. Large
Yes, I
language
know.
models are really, it's everywhere right now, which is I think I just heard like it's the 30 or 35% of the, of the venture capital running on the, in the, the entrepreneurs today. I think a couple things we are looking at with our team. I'm not sure Enis is here. We are looking at first and foremost how the most important problem of the AI is the cleaning stage and how you get a good data, right? LLMs can be great help for data cleaning and data pre-processing, and this is the one of the great inputs. A lot of inputs are a lot of research is going on right now. How you create a synthetic data and how you clean the data for your use. The LLM is very useful for that, and we have started a research on this. We are using LLM to pre-process and clean and just collect the synthetic data where actually the most problems is the good and reliable data, where you can get the good and reliable data. So that's where we are working on LLM. This is number one. Number two is you can use also LLMs comparing to other things like LSTM, all those traditional techniques. Yeah, if you have the lots of data and good data, the LLMs basically can also help here, but it's not that clear because there are a lot of hallucinations and things like that in that regard. So I think that requires more research. But the more important one, on top of these two, actually, you use the LLM as an interface to the techniques that what you're using. So you can have the like a your factory floor, your how do you say the picture of your or figure of your assets, and the right and left hand side you can ask like NLP. You can ask questions about your predictive maintenance. You can ask the details. So you can. I think the LLMs can be the first use of LLMs on top of the other technique. Good uses are the interfaces. You can ask in text, right? What is the remaining useful life of this battery? You can ask what is the factor of these inputs, and then you can hook up, link those explainable AI algorithms to those texts. Then it can give a great output and good interface to your algorithms to make it more explainable. That's what I think. I think these three in these three domains, LLMs will be useful, and I think we are just starting it. We are just starting researching it. As the other
Serdar,
researchers.
thank you very much. We will continue this topic in the brainstorming session because
Thank you.
we are all aware of the advantages and what it can bring, the LLMs and its uses.